So it's my
Let's
great
get
pleasure to have Misha Sra giving us a presentation now. She's from the University of California in Santa Barbara, and she does really amazing work in the intersection of AI and HCI. She's going to be talking about that today, and in particular, talking about designing human AI interaction. So I'll let you take it away, Misha, and I look forward to your presentation. Thank you so much.
Okay, great. Thank you for the introduction and thank you for having me. It's good to meet everybody online and in person over there. I am really excited to be here. So, starting with at the Human AI Experience Lab, we design, we build, we study new types of human AI systems, and as the talk title says. And specifically, we're looking at these systems that can enhance not only our daily activities, but also our abilities. Let's see. All right, so building tools we know that enhance our abilities is nothing new. As a species, we've been doing it for 3.3 million years. Stone tools way back then gave our ancestors a lot of new physical capabilities. And then about 5,000 years ago, well, not 5,000 years ago, but the mastery of fire transformed uh, human brains and allowed them to do a lot of new things. And then the invention of writing about 5,000 years ago gave us the ability to store and transmit knowledge. Now, the digital revolution of the last century, so fairly recent in terms of if you look at the timeline from between now and 3.3 million years ago, it has dramatically expanded our ability to process information and to connect globally. And AI is part of this digital evolution, and now I believe it has the potential to do so much more. Fundamentally, I think that traditional tools in general, whether it's a hammer or it's a laptop, I'd like to describe them as command executors in the sense that they remain idle until we act. We execute some kind of we ask them to do something, and then they execute some fixed predetermined transformation of our input. And in contrast, I like to think of AI as this dynamic and potentially self-improving system. We still direct its goals, but it can learn from every interaction. It can tune itself to our context, and it can take initiative instead of just waiting for our commands. And I think it's this ability that gives it the potential for taking out something like even a social role, becoming a collaborator, a coach, or an instructor. My slides are progressing, right? I'm on slide 4 right now. It says AI interactions are command centric.
Yes, we can see your slides. It's going great.
All
Thank you
right,
so much. Yeah,
perfect.
perfect.
Right. So, despite this potential that AI has, our interactions for engaging with AI are very, very command centric. And our interface are practically flat in chat. Right. You can see examples of the main ones out there. But what if instead of this, we could do this? What if we could embed AI directly into our environments and we can extend its impact far beyond the computer tasks that we do sitting at our desks and on our screens? And I think that has the potential to unlock new types of solutions for people who are on the move, people who are on the go, as new kinds of problems unfold and appear when you're away from your desk than when you are at your keyboard. Here's some examples of scenarios that I'm imagining. For example, today's AI we know is confined to flat 2D screens, but the world we live in is 3D. It's dynamic. And for AI to be able to serve as a true partner, whether it's going to be a trainer, a mediator, an instructor, a co-creator, a therapist, like any role, it kind of needs to meet us where we are in the real world, moving and doing things, right? So if you look at these scenarios where I'm learning, or a person is learning to do perform surgery, or is getting assisted with physical therapy, you can sort of imagine the disruption it might cause when you have to pause mid-task, stop, and then type in a query to ChatGPT, or even pause to ask a query. We can imagine these scenarios for it to be proactively watching what we're doing, offering assistance when needed, but then staying in the background when not. And so embodied AI in that sense, I can imagine can help keep the guidance anchored to the user's workspace and then freeing up their hands and their attention for the primary tasks that they're there to do, not having to direct all their attention or even a large part of their attention to just managing their assistance with AI. Now our interfaces with AI, I believe, are the way they are because they're designed around algorithms. They're not designed around people. If you look on the left-hand side, the current approach to build AI systems is fundamentally to build them in isolation from human users. There is some kind of benchmark that has been prioritized. And while I understand we do need our fundamental models to get better, but in terms of applications, also similar things are happening. Right? So there's a prioritizing of benchmarks over human needs and of our experience. And this can force us as people, as end users, to adapt to rigid tools that get thrown our way, leading to poor usability, ethical concerns for sure, and then, of course, a lack of trust. Now, our approach in our lab is to design AI that is centered around human needs, right? An iterative approach, the usual approach that you would take if you were doing any kind of human-computer interaction project, looking at people's behaviors, their ways of thinking, and then ending up with systems that are truly intuitive, relatable, and actually helpful, things that people would want to use because they are solving a real need. And so if AI truly aligns with our needs, I imagine it can help foster growth. It can safeguard our autonomy, something that a lot of us are worried about, and then enhance our resilience. And so in the rest of the talk, I'm going to present a few projects from my lab, and they fall into each of these categories. And then I'm going to conclude with a little bit of a vision, what I think of what the science of human AI interaction could be, and then other directions of ongoing research in my lab. Okay, so let me begin with this first area of growth, and I'm going to present a couple of projects here that are focused on supporting learning and continuous development. So this work on AI-generated characters for supporting personalized learning and well-being emerged from our own experience of learning and teaching during the pandemic. As many of you may have experienced, it was a time when students were learning sitting all by themselves in their wherever they were, and there was hardly any motivation to get onto Zoom and go to class. And so we started looking into how might a personalized AI system motivate learning and curiosity? How could it enhance effectiveness and well-being? So fundamentally, how could we actually use this new technology at the time, right? Deepfakes were a thing, which they still are, but the use for negative was overshadowing positive applications. Now, to be able to ask these questions, we needed to first develop a system, and which we did. So we built a machine learning pipeline that can create personalized pedagogical agents, as you can see, Einstein on the far right. And we also designed a conversational system as a follow-up, which I'll talk about in the next project. So the input to this pipeline could be anything, video, audio, text, and then it will generate a synthetic voice. It will generate a talking head video on the right. And we also thought about watermarking the output so that people could tell the difference between what's generated versus what's actually recorded video. Here are some examples of output that we created. And again, we were asking the question of how might learning from any of these characters enhance your own learning motivation? Now, to answer that question, we actually did a study where we looked at what happens if we let people learn from characters they want to learn from. And at the time, we wanted to pick someone controversial, someone who elicited strong emotions in people, and see how that might impact learning. So this was what our study looked like. We had 134 participants, and we did an online study, and there were two parts to it. There was a lesson followed by a survey and then a quiz. And our two independent variables were the degree of liking and the degree of admiration. So in the left, you can see is a recognizable individual, and people may have different levels of liking or admiration for this individual. And the control group on the right, that character kind of sort of looks like the experimental condition, but recognizably is different. Right, so the kinds of questions we're asking, the dependent variables are looking at learning performance. We're looking, as I said earlier, motivation, emotions, and perceptions of the virtual character. And so when we look at quiz scores, right? It was a 15-minute lesson followed based on the World Health Organization's lesson on vaccines. And again, this is COVID era, so it was the topic of the times. We didn't see any significant difference in quiz scores, but we sort of see a moderation, admiration appearance, or moderate appearance significance for admiration. And so there's many reasons why we could speculate this might have been the case. There's novelty happening and the topic was possibly too simple. And we certainly need more longitudinal studies to figure out an actual impact of what's happening than the one-time study that we did. So looking at motivation and the types of questions we cared about answering was whether a person was motivated to pay attention to the lesson they just watched, or they would like more lessons like the current lesson, or they would like to learn more advanced material from this particular instructor. And lastly, if they put in a lot of effort to understand the information in this lesson, we see significant increase in all of those. And this is even when we told people that they were learning from a virtual character. And at the time, of course, and much different from now, there were visible artifacts in the mouth movement. So it's not like you couldn't tell it was not the real person. You could, but we still see the effects. All right. Oh, and wait. Right. So in terms of emotions, we see positive significance for the instructor made me feel happy and the instructor made me feel content. And similarly, the instructor made me feel frustrated was not the case, and the instructor made me feel bored was also not the case. And then lastly, the third research question we leveraged the use of the agent persona instrument to measure the learner's perceptions of the pedagogical agent. And the idea was, prior work has consolidated these measures into four main categories of how well an instructor facilitates learning, how credible they are, how human-like they are, and how engaging they are. And we saw significance in both the liking condition and the admiration condition across each of these dependent variables. Now, yes, the results are promising, but as I said earlier, there's possibly novelty effect going on. The study was small. It's only 134 participants. It wasn't longitudinal, etc. And then there's a lot of other things that we need to consider when we're using generative AI for something like this, right? There's clearly the risk of disinformation. I mean, we control what the character says, so it could say anything. There's obviously privacy and consent issues, like how do you seek consent for deceased people? And then the whole idea of we're not really looking at replacing anybody, but supplementing instruction. And then what happens? We don't really know if people would be willing to learn from this particular individual for a long, long time, or is it maybe going to last only a week and then they're going to get bored and move on, and then or whether they're okay learning lots of different material subject types from the same instructor. Like, should Einstein be teaching French if you want to learn a different language, or should Einstein stick to relativity, or should Einstein teach something else altogether? Like, none of those questions are answered yet, and all open to further exploration. So working on that project got us thinking about what we could use these tools to learn more about the past, since we are already creating these pedagogical agents of people who are no longer with us. And the idea was that maybe we could do this in a more interactive manner. So beyond just being able to read about somebody, for example, like Leonardo da Vinci, can we actually talk with Leonardo da Vinci and learn about their ways, their wisdom, and things like that? And so that got us to building this system. And again, like the previous work, we first build a pipeline and then we do an evaluation. And so in this case, our system was twofold. The top part of the system is the same as the previous system, where we have a talking head of Leonardo da Vinci. And then the bottom part is where we have the new component, where there's Leonardo da Vinci's original source material, right? The journal text. And then when a human asks Leonardo a particular question, then we use a semantic model to look through the original source material to find the relative possible responses. But these responses then we feed through GPT-3, which was the model available at the time, to convert it into more conversational like output. And we don't quite stop there. this conversational output, then we again do a cosine similarity with what is in the original journal. And the idea was that, we don't want the model hallucinating and answering anything that is too far from what Leonardo actually wrote about in the journal. And so this architecture, as you may be familiar with, is now called RAG. But at the time when we worked on the project, we didn't know of any such framework. And now it's pretty commonplace to reduce hallucinations using RAG. So here's sort of examples of the kinds of questions that we could ask, and then the ground truth as it's listed in the second column, and then a comparison between just simple fine-tuned GPT-3 and then our model, which is a combination of the semantic model and GPT-3. And as you can tell in the second row, Leonardo technically shouldn't really know what the United Nations are or is. And so our model says the right answer, I'm not sure, but GPT-3 just has an answer, right? And that's sort of what our method is preventing, for it to be able to answer about things that it has no clue about. Or technically, Leonardo should have no sense about all the things that happened post Leonardo's death. So since these kinds of systems are still relatively new, there's another contribution. We wanted to do a new kind of metric method for evaluating the accuracy of these, what we're calling living memories, in terms of their question answering capability. And so we created a data set of 600 question answer pairs, which were generated with our pipeline. And here in the results, you can see that our architecture is outperforming baselines on accuracy, on style, on understanding, and on grammar. And these metrics are metrics that we devised in an earlier paper that we published in AAAI in 2022, in which we focused on style transfer between a doctor and a layman to be able to make that conversation more intelligible. So this study was done with 86 participants who all rated the answers that all of these models provided on a scale of 1 to 5. And so we're only showing the set of answers that got higher than 4 score. We also did a study with end users to see what the system feels like, and what the interactivity feels like. And in this study, we again had 90 participants, and in the first condition, the participants interacted with the living memory of Leonardo da Vinci. And in the second condition, the participants were just reading about Leonardo da Vinci. And so the chatbot experience essentially is a 40-second long animated video of Leonardo da Vinci introducing himself, generated using our pipeline. And so the equivalent was reading about da Vinci, and then the third condition was reading about Da Vinci and then interacting with the conversational Da Vinci. And as you can see the results, that for curiosity, for learning effectiveness, for motivation, the condition that actually mattered most was the last one. Okay. And so the results are showing us that living memory has the potential to increase curiosity, effectiveness, and learning about Da Vinci and motivation. And I think the most interesting result is the fact that the interactivity gets added on and introduced as a new learning modality, that it is not replacing existing modalities that people already use. And I think that's kind of a interesting finding here. Right? And same as the last work, we have all the challenges when it comes to designing systems like this related to consent and privacy, to authenticity, and even talking about what does it mean post-mortem existence. And I sort of caught the tail end of Saranga's response to one of the questions being asked, and he mentioned reincarnation, and it kind of sounds a little bit like that to me when we're talking about post-mortem existence, right? And then again, the idea of supplanting teachers, or what happens if it leads to overuse or addiction of some sort, or if these characters that you look up to, that you want to learn from, start now promoting negative things. So all the things that need to be thought about before we actually put something like this in actual broader use. All right, let me turn to the next area, autonomy, and present, I think I'm only talking about one project here, that is looking at empowering self-directed achievement and independence. We know that more than half the global population plays video games. And gaming in itself is a much, much bigger industry than pretty much everything else combined. Movies, sports, etc., music, everything combined. But it's also not quite as equally available to everybody as we might imagine. Right, so this is my student. She graduated last fall and she is now a postdoc at CMU and she has spinal muscular atrophy. So fundamentally, she has no voluntary control of any muscles in her body except her right thumb and her facial muscles. And so as you can imagine, video games could offer a way to build community online. But it is not possible. It has been challenging to actually be able to play video games. Right? And of course, there's many reasons to play video games beyond building community, entertainment. It could be education, it could be rehab, all sorts of skills that could be learned. But games are demanding. I mean, fundamentally, you do need your hands to play most games, or at least you need some physical input. If you're playing or were playing on the Kinect, then you needed your body. But otherwise, on the keyboard or the gamepad, you need your hands. And video games are not particularly accessible to those with hand motor impairments. And so while game systems have a lot of accessibility features, the fundamental assumption is that you are able to use the controller to some degree. There's a lot of different devices out there that are built for people, or it could be used by people with motor impairments. They could be BCIs or brain-computer interfaces. You can do voice recognition and gaze tracking. You could have just a single button switch, tongue-based interfaces, and then the quad stick, which is the main, at least a product in the US that I'm aware of, which is a mouth-based joystick that allows you to play. And each of these systems have their pros and cons. And fundamentally, when we were talking about designing a system, we wanted to, first off, not build games that are specifically built for somebody who has SMA. We wanted to be able to play any games that everybody else is playing out there, like FPS games or car racing games and of the sort. And second, didn't want to wear a device, right? SMA itself, because it's a muscular disease that has its own fatigue challenges. And so didn't want to wear something that required equipment to be worn and then was slow and unresponsive, had high error rates and whatnot, which a lot of these do. And so we ended up deciding to build a system where it uses facial expressions as input. And while we do use a little bit of speech input, we don't use it for game actions. We mostly use it for larger things like start, stop, because it is a little bit slow since it does processing in the cloud and comes back down. Right, so facial expressions get mapped to keyboard input, and then those get mapped to the actual character motions in the game, whether it's moving forward, back, turning, shooting in an FPS, or turning left or right in a car racing game. So for those of you not familiar with how facial expression recognition works, the face is fundamentally coded by a system called the Facial Action Coding System, or FACS, which is an anatomically based system for describing all visually discernible facial movement. And it breaks down the facial expressions into individual components, which are called action units. So these are muscle movement components. And on the slide, you can see two of them. Action unit 6, or AU6, is cheek raiser. So these muscles are being raised, and that's one AU. And it's bilateral, both sides of the face. The cheek muscles are being lifted up. The lip corner puller is AU12. So AU6 plus AU12 leads to a smile, and then the interpretation of the smile is a positive emotion. So that's kind of what we were using. We were using combinations of AUs to act as input for particular character motions. And after building and testing the system with the student who built it, also, we did a study with 12 volunteers who each had either muscular dystrophy or spinal muscular atrophy. And because each individual, again, these are muscular diseases, fatigue is a huge challenge. And my student who's doing the study also has to manage her own fatigue. The study took place over 2 Zoom sessions. And we installed it, whether the person at the other end had a caregiver to help install or they were able to install themselves, and then ran through the study. And what we had done is build a customization interface so that the participants could actually change what they wanted their facial expressions to be able to do. I mean, our mapping was based on what made most sense to the student, but we wanted to give the other people ability to choose the mapping and customize the system. Right. So in general, I mean, the participants were surprised that our system did not depend on using hands to play video game, and yet they were able to play something like an FPS. And so we evaluated in general on usability, and then we looked at learnability and sensitivity, ease of use and comfort, right? We're just looking at survey data here. And for all of these, you can see the ratings are fairly high. And this was 8 participants. We also looked at participant data on the game itself. We're not particularly great game designers. We just had a very simple FPS with zombies and things like that. But still looks like participants did enjoy playing the game. And what we didn't have is their ability to change the game's difficulty. The difficulty was tuned to the student who built the project, my student, but I think that would be helpful because for some people, as you can see, the tension wasn't that much in the game, and they might have had higher tension in the game if they wanted, if there were many more zombies coming at them much faster than they were otherwise. Right, but these are all easy to tweak. And what we also did was try out our system sort of and see if it worked with any of the games on Steam. And we tested 4 different games and it kind of worked out of the box. We didn't have to do any changes to anything. As long as games allow keyboard mapping, the system is usable. Excuse me. So here's some of the qualitative feedback from the participants, which was encouraging to see. And our hope is to be able to just upload this, release it publicly so people can, family members, friends, etc., anybody who wants to take it forward can take it and use it as they want to. I'm going to show a short video.
Option 1. Jump. Reload.
Okay, moving on to the last area of resilience, I'm looking at projects that are designed to empower individuals to adapt and to flourish. So spatial memory we know is fundamental to real world functioning, and spatial navigation necessitates the temporal integration, the preservation, and the evaluation of many different spatial cues. And so there's a lot of prior work that shows that galvanic vestibular stimulation, or GVS, can boost spatial cognition in people with vestibular disorders. Its effect on healthy participants are a lot less explored. And then a lot of the studies in previous works have used desktop tasks, where even though the objects are laid out in 3D, you are not looking at them from a first-person perspective. So they kind of lack the scale and immersion of real world, which is why we did our study in virtual reality to try to make it a bit more ecologically valid. And for those of you not familiar with GVS or vestibular stimulation, you fundamentally put electrodes behind your ears on that bony part, and you electrically stimulate the inner ear that's responsible for your balance and your sense of up and down and things like that. So in our study, we built a multi-stage navigation task, which was in VR, which sort of tries to mimic the real world demands when you're doing search in the real world. And some participants were asked to sequentially locate the positions of these colorful glowing fires in this virtual environment. We had 32 participants, and it was a between subject study. So we had GVS, a two-part process, right? First, participants go in and they have to look around to get a sense of where the fires are located, and then we remove them. Then they go back in, and now they have to tell us where they remember where they saw the fires. And so we had just measured data, we have path lengths and time to completion, but we also have questionnaire data and whatnot. Okay. So for each pair of consecutive coordinates in the path trajectory, we calculate the Euclidean distance, and this is how we figure out how much distance each participant's walking. If you look at the graph, we can see significant difference in the path lengths between those in the with GVS condition and those in the without GVS condition, right? Those in the with GVS condition, the orange is really, really small. So the difference is quite significant in the path lengths. This is another visualization of the path length heat maps. So here we are basically just projecting down to the ground plane and trying to see where participants were walking in the scene. And the orange row at the top is showing those in the with GVS condition. So we're using noisy GVS, not directional GVS. And paths appear to be a little bit more direct. You know, you almost can feel like they kind of knew where they're going, and that's where they're going. Whereas in the without GVS condition in the bottom row, people seem to be meandering a little bit more and sort of doing a little bit more of a, is it here? Is it here? Should I go there? What do I remember kind of thing. Looking at time to completion, we again see a significant difference between those in the with GVS versus the without GVS condition, right? So this, I'm trying to remember, this is looking at all the fires that they found, not just one fire. So this is aggregate time taken. And we didn't really give participants any specific time. There was no time pressure. The task was open-ended and they could take as long or as little as they needed to until they found all the fires. So there's this one challenge in our study is that GVS and VR, as we know, can have a positive impact on reducing motion sickness or cyber sickness. And so now the question is it the reduced cyber sickness that was helping participants do better? Or is it GVS has some other pathway to assist them? And so while prior work shows that the pathways are completely different in the brain, the signal is the same, right? It originates in your ears and it's going to different parts of the brain. So there's likely some impact of the reduction in motion sickness. And while we did ask all our participants about their motion sickness levels and nobody had high levels of motion sickness, we can't entirely discount. And so fundamentally, I think future work that we're looking at now is doing a study where we can try to isolate this impact on motion sickness from this impact on memory and try to disentangle both of those. We also did analysis. I mean, the paper has a lot more results. We looked at gamers versus non-gamers, and we didn't really see any difference over there. And whether it's time to completion or path lengths, we looked at people. So initially, before the study started, we had asked everybody to give us fill out the SBSOD questionnaire, which is the Santa Barbara sense of direction survey. And we didn't see anybody, like people who said they did well over there didn't particularly do any better or worse in the study task. So we didn't really see a correlation there. All right. So I guess to end this project is to say that, we still need to disentangle some motion sickness effects, even though we understand that the brain pathways for memory is hippocampal and motion sickness is completely different pathway. And that's sort of what our current focus is. And continuing on to this other work, this is an augmented reality system for facial paralysis, and again builds on this notion of action unit or AU intensity estimation. And the difference being that in the previous project in facial expression recognition, we're looking at action units, they're described as bilateral. So both these cheeks lifted up as AU6. But in facial paralysis, where one side of the face droops, we wanted to look at unilateral action units. So this is independent of this, right? And so facial paralysis, if you are not familiar, is a consequence of many, many diseases. It could be stroke or brain tumors, but it impacts one side of the face, which leads to drooping. And so you can imagine that it leads to difficulty in talking and eating and communicating and blinking or making any kind of facial expressions, which are fundamental to our communication with each other. And so it can cause significant emotional distress and lower people's quality of life and their psychosocial well-being. From our understanding, the state-of-the-art therapy is mirror therapy, where patients or individuals look at their face in a mirror and they have to perform a specific set of exercises at home. And then they go see their therapist every so often as they need to. So the challenges were that mirror therapy, I mean, you get biofeedback, but you don't have any other way of tracking progress. And in general, looking at your face continuously for people was stressful and anxiety causing. Technically, our challenges were that there were no data sets or no particular trained models. And then everything out there that is to do with facial expression recognition looks at AUs bilaterally. And what we needed to do was detect them independently. We also needed to build something that would provide real-time feedback and be able to run on a mobile device and run locally and not process in the cloud for privacy's sake. And of course, it needs to be easy to use for potential to actually be used. And the solution was to develop a new kind of lightweight model, which is based on the intermediate layers of another existing model, which was a heat map based model to figure out what action units are being moved. And so compared to that particular model, our architecture was much, much simpler and saved about 99.7% space, which is how we were able to run it on a mobile device and still have fairly high accuracy. So we predicted action unit intensities independently for each side of the face and then calculated a ratio to figure out if a particular action unit on the paralyzed side of the face was overactivated, underactivated, or optimally activated relative to the same person's other side of the face. An important characteristic of anything to do with facial paralysis is sort of learning or education of facial muscular anatomy. And so we put you can imagine Snapchat, like augmented reality filter on the person's face so they could correlate which muscles they were being asked to move, as in this visual, and the feedback that they were getting at the bottom, telling them how much they were moving that muscle and whether that was moving in the right direction or not. So here's a little video that tells you, as the person is smiling, we can see each of the action units that are at the bottom, how they're activated. with green being optimally activated, purple being overactivated, and blue being underactivated. And so when we did a study with 20 participants, we had them perform 5 facial exercises, and participants was split 50-50 across Android and mobile iOS devices. And at the time, because this was the first study we were doing, we mostly wanted to see general acceptance of this kind of system for therapy, and what they thought the usability in terms of experience, like what they generally thought about the efficiency of the system, whether it seemed reasonable to them, whether it was when something that they could use, and how it might compare to mirror therapy. And from a qualitative feedback perspective, no, participants did say they found it better than a mirror, and they thought it was motivating, and the fact that they could use it anywhere and everywhere being on their mobile devices was a positive. And so now we're continuing that work. We have the next version. This one, as you can tell, was only 4 action units. Now we're doing 22 and trying to build an app. Of course, the model's much bigger this time around, a lot more action units, and trying to run it on a mobile device a lot more challenging. And that's sort of where we are at the moment. And that work's being done in collaboration with a facial surgeon from UC San Francisco. All right, here's sort of some examples, and I think I'm going to skip. This is sort of hardware work that we continue to do at my lab, and these are also sort of looking at, whether it's building a pressure sensitive glove or a headband to capture facial expressions and pupillometry or other kinds of haptic feedback for VR. All right. So in looking at the last part of the talk, as you can all see that these 3 areas that I just talked about of growth, autonomy, and relatedness, they sort of allow us to conceptualize the future, at least from my perspective, a science of human AI interaction, where we can design systems that are more integrated with humans and those that can eventually lead to augmenting our daily activities as well as our individual potential. And I like to define the science of human AI interaction as a study of how humans and AI work together as components of a cognitive and a sensory motor system. And as I said earlier, that I think AI's value lies not only in helping us with screen-based tasks, but also coming out of the screen into the real world and assisting us where we need it for actual physical things that we're doing, from sports to surgical education to rehab therapy and whatnot. And so to ground this science, I draw from 3 foundational theories. The first is the second self, Sherry Turkle's work from the 80s, the media equation, Nass and Reeves from the 90s, and then the distributed cognition theory from the 2000s. Sherry Turkle in her work shows us that tools don't just support thought, they shape how we think. And so fundamentally, that means that the tools that we use shape the kinds of questions we ask, which then shapes the kinds of problems we solve. So a lot of this reciprocity exists between us and our tools. And as an example, if you look at a paper from Sparrow, Liu, and Wegner from 2011, they showed this whole notion of, or they call this the Google effect, right? Which is fundamentally that our focus shifts from remembering where the information is found, shifts to remembering where the information is found, as opposed to focusing on the information itself, right? So we kind of know how to find things, but we don't know what is it that we found. Another example is GPS, where we're outsourcing route planning to this other device, which means we're not really using spatial reasoning and making a mental map of where we are, where we're going. And so over time, what we're doing is learning to follow instructions more effectively, and which uses different parts of the brain compared to actually building this spatial map, right? So the tools are impacting how we are evolving and changing, and they are shaping how we're thinking. Nass and Reeves established this idea that people treat media, which now, of course, AI, as social actors and responding to them with the same types of social rules and expectations that we apply to other human beings. And so this idea, I think, has profound implications for the design of human AI interaction. And we've seen a lot of this in prior work in VR, where proxemics and other social norms are maintained with avatars, even though people know that this is a computer-generated entity and it's not a real human being, that you could kind of walk through it, but you don't. And then lastly, Ed Hutchins provides us a framework for understanding how our thinking is distributed. It's distributed across tools, across people, and across environments. And that cognition isn't this isolated process that happens just in our heads, but where we are and who we're engaging with, and all of those are involved in this. And so designing interaction is, I believe, as critical, designing interaction with AI, as the designing of the intelligence itself. And so these sort of three theories, I believe, feed nicely into this idea of how we can even conceive of a science of human AI interaction. Right, so to sort of bring it all together and summarize, right, we live in a complex world, we know, a dynamic world, an world full of objects, tools, places we go, people we interact with, things we do. And every day we engage with this rich environment through multiple modalities, from our sensory modalities to talking, to motion, to social interaction, to emotions. So as the visual shows, this is our engagement, the human world interaction. But despite AI's promise to enhance our lives, our interactions with AI remain largely confined to a screen and typing into a small text box, so using a very, very thin bandwidth of our abilities to interact with entities. And this separation, I believe, highlights an urgent design challenge that we need to develop human AI interfaces that can seamlessly integrate a larger bandwidth, right? And as you can tell, I'm not going all the way to human because I think we're not building humans or new humans. What we want to do is be able to engage with AI to a greater extent, right? So larger sensory abilities to be able to engage with it is where I would like human AI interaction to be. And so looking ahead, and in fact, ongoing research in my lab is looking at several of the directions that focus on addressing this fundamental question of, how do we increase this bandwidth of human AI interaction? How do we design AI as this multimodal spatial presence that can support our needs in everyday contexts? And so we have ongoing work that's looking at what's beyond the chatbot and what are some new ways of understanding human agent interaction. And should we be designing human AI interaction or human agent interaction to mirror some ground truth we have of human-human interaction, or this is a completely new thing? And then we're looking at applications of AI or agents as different social roles, as I mentioned earlier. And then also continuing work on using AI for designing new types of systems for rehab. So one area that we often discuss in the lab is what I call lifelong human interaction or human AI interaction. And this is more a thought experiment. It's not like, the idea is that what happens if a baby is born and an AI gets born at the same time? And now the AI and the baby, AI is there to support the baby, and the AI's role will evolve as the baby grows into a kid, into a teenager, into a young adult, and into an adult, and all those things. And the AI's role might change from support, assistance, to guidance, to reflection, to all of those things. And so this is, of course, there's lots and lots of challenges. I'm not even talking about engineering challenges, just ethically and all those things. But it is an interesting topic to think about. All right, just to wrap it all up, so the research I shared today, the projects that I presented, I think of them as sort of just the beginning. And at the core of our work at the lab is this deeper goal, not just to build more effective human AI systems, but to actually build systems, in the words of Kleins and Klein from 1960, that can create space for humans to explore, to create, to think, and to feel. And I truly believe that the value of AI lies not in what it is, but in what it enables us to be. With that, I think I am going to stop and happy to take any questions.
That's amazing. Thank you so much for your presentation. Really, really good content. So just let's open the floor for some questions. So I'll just open the chat window here. And does anybody in the room here have any questions for Mishra? There's one question I had, which I thought was really interesting, was the thought experiment you posed just right at the end was, when your baby's born and AI gets born at the same time and grows and develops as well. But of course, the pace of technology is so much faster than what um, as humans grow. Like if I look back to my birth year, when computers were the size of houses, and now they're in our pockets. So what do you think the implications are for having AI that is growing exponentially as and helping a human who's growing linearly, I guess you could say.
I mean, I can imagine when I say that AI is born at the same time, it's sort of like more spawned like a video game character spawns. Like there's systems out there, and then we have an instance of that system that is designed to grow with the baby, assist the baby. And it is I mean, I imagine it more as something that will be constantly, like any other tool we have, it updates and it changes and
Mm.
evolves. But to be able to sort of be the same but different as every update brings changes, and some might be destructive and some might not be, that there will have to be some system of constraints that these updates function under, that the AI's personality doesn't entirely change or becomes a whole new entity that is unrecognizable to the, let's say, not the baby, maybe the kid or someone else, whoever's partner this AI is. But it's at this point, like I said, it's very sort of science fiction-y in my head, and conversations we've had in the lab, and it's lots and lots of challenges. But it's sort of an interesting thing to think about, as to
Yeah.
what would it mean through the life cycle of a human being for this external entity to have sort of a stored memory of that human from a third person perspective. And what would it mean for, let's say, assuming people still have Alzheimer's and dementia when something like this is a reality? Like, would it actually be able to assist and come up with therapies? Because now it has a memory of the person's entire life. So
Great. Yeah. And there's a question on the chat from Josh. And one of the first growth studies you presented was the objective tested data. Was the objective tested data in response? Was the objective test data collected in response to the learning materials? In addition to the self-report case scales, apologies if I was there and I missed the graph, but curious whether it was showed material was better regained if the user felt positive effect towards the AI character. You can read the question in the chat as well. So
and I'm looking at it. Yes, we did collect test data because participants did take a quiz, and as a result showed there was no particular difference in the experiment condition and the control condition for the quiz results. So we saw more differences in terms of motivation and emotions, but not in terms of the material itself. And I feel like because there's got to be as likely some impact on novelty effect there, that if you're learning from an entity which we've told you is AI generated, and the whole idea is relatively new, that you're likely paying a lot more attention to the material than you may otherwise do. And so I think longer term studies would probably give us a little bit more insight into what actually might be going on there than our one-time study.
That's very interesting work. Especially the notion of having people out that aren't experts talk about subjects, or experts talk about subjects outside their area of expertise, like
Yeah,
Einstein teaching French, for example.
yeah.
I think we have a lot of problems in society today because people attach universal expertise to people that are really only expert in one domain. And Zhuang has a question online. Zhuang, do you want to
Yes,
unmute yourself and ask your question?
yes, ma'am. Thanks. Thanks, Professor Misha. Really nice talk. Actually, like this should be my second time to listen to your talk. I think last time it was in VRST 2023. Your topic was
Okay.
about human
Hopefully there were some new projects this time, not all the
AI.
same.
Sure. Yeah. So actually, I have two relatively general broad question. So first question is like um, what are the key differences you think between human AI interaction and the human agent interaction? And second question is, can you please share those insights on research direction of combining XR and AI agents? Thank you.
Okay, I'm just going to repeat the questions to make sure I understand. The first one is, what are the differences between human AI interaction and human agent interaction?
Yes.
Yes. At some level, I think there is no difference because it depends on how we create an agent, right? So right now, let's say you have agents that we use online. They are fundamentally representations, but they are task focused of the AI that's running them. So in that form, it is an interaction with the AI itself. The way I'm imagining agents is that you are wearing an AR or VR headset, and then the agent gets visualized. Like it's actually an agent, like, it could be a human looking visualization or whatever it is, but there is an entity that is now occupying space in your physical space that you can see it move, that you have this shared pointing at objects and you have a shared context. So I think of agents as that, but the agent is driven by an AI backend. And so interaction between the two, I kind of think, in my head, they're synonymous. Okay. Could you repeat your second question? I'm sorry.
Sure. Yeah, so the second one is, can you please share some insights on research directions of combining XR and AI agents?
Okay, any research directions, right? So as I was saying that one of the research areas we're looking at in the lab is AI beyond the chatbot, right? And it goes to the same idea of what really happens when you start visualizing AI. And, if you look at online platforms like Character AI or Replica, there is some visual, but it is sort of a icon or something else like that. Or if you look at it in AR mode, it's a little avatar. And I feel like when communication with an entity changes from typing to conversing, the types of conversations that are had change. The way the conversations happen also change, right? Because typing is necessarily differently effortful than conversing is. And typing requires maybe you're doing some thinking, you're also discretizing your thoughts as you're typing them down. Whereas conversations, you can think of it as a little bit more of a continuous flow of your thinking. And so as one example or direction, I think I'm interested in looking at is that what happens when you visualize these agents, again, in AR or VR, whichever have you, to occupy space and sort of now play a social role as, let's say, a coach or a peer or a mentor or a therapist or whatever role, right? And then compare it with something that's not visualized in a similar way, but you have access to all the same things, right? What is going on over there? And as I said earlier, is now human to agent communication, should it be grounded in human to human communication, interaction, mannerisms, behaviors, or should there be a new type of language emerging of how you communicate with agents? Because you could have all sorts of shorthands, right? When we do messaging online, we use emojis. We don't have to type everything. You don't have to explicitly say, I am feeling A, B, C, D, E. You just put in an emoticon. And so is there something like that might emerge in a communication with AI? Because it doesn't have to be quite as verbose as communication with humans needs to be. I think that might be another interesting direction to explore. So those are like kinds of things we're looking at in the lab right now.
Thanks.
Thanks for that.
Sorry, I might have another kind of follow-up question. So, as you mentioned, like how the research might mainly mimic human interaction while researching human agent interaction. So, do you think human agent interaction should always like keep mimicking human interaction, or there could be other options or possibilities?
That's kind of what I'm saying, right? That in general, the assumption is that the human interaction is sort of the gold standard that we're building towards. Like this is how it should be, kind of thing, right? This is what we're benchmarking against, perhaps. And that applies to human AI collaboration, that it should work just as well as human to human collaboration works when it does. And I think my question is, well, one, we don't have any other thing to go by. We only have human to human to go by. And that's fine. That's a good starting point. But I feel like that it doesn't need to be constrained by that. That by experimenting in that space, we can develop the human AI communication can have its own kind of language, its own kind of jargon, its own kind of mannerisms, whether they're social, learned from how we treat each other to maybe not, because we know it's an AI, it's not a human being, right? Are there going to be new types of social norms that come out of this interaction? So I feel like all that remains to be explored.
Thank you. Thank you so much.
Thank you for that. I had one question as well. The results you showed from the galvanic simulation were really interesting in terms of how people, and compelling in terms of how people were able to have more spatial memory. Why do you think that is working like that? It was really interesting to me.
Oh, the vestibular stimulation. So I think there's
Yes, the
prior work.
sorry, yeah.
My this is just my own hypothesis is that, you know, anytime we do anything in the real world, of course, our head is involved, our eyes are involved, and that means our vestibular system is involved because we're constantly looking around, turning our heads and doing our things. And so when we're doing, let's say they did the initial walking task in VR and they looked here and they looked there and all these things happened, the vestibular information is also part of input, let's say, to the brain, right? You remember that you looked left and turned left and there was something over there, or you remember you turned right and there was a red fire over there. And so when during encoding of the memory, that information is automatically part of your human behavior. That's what you're doing, you're looking around. And during decoding, I feel like that the stimulation to the GVS system actually, in some sense, jogs that part of your memory. And so the hippocampus, as I said, is involved in spatial memory, that it gets more information than it otherwise does. You have this extra added GVS information that you didn't have before. And so that's kind of what I think is happening. But from a neuroscientific basis, I don't know the details of what exactly might be happening, because when you're stimulating with GVS, you can't selectively stimulate anything inside your inner ear. You're basically stimulating everything that's in your ear because you're doing it externally, right? So that's a very, very interesting and a valid question, and something that, you know, I'd like to dig a little bit more into, and hopefully with some neuroscience collaborator who has a lot more information knowledge in this space than me.
That's interesting. And then, of course, you can decouple it from the motion sickness. I guess
Yeah.
one thing you could also do in the future is have people not move their head, but have the world rotate around them, and decouple the head
Oh,
motion from the from movement. So you could use a
yeah, I
joystick
think
or
it's a
something, and you
great
can
idea.
drive the world around people rather than turning the head. Yeah, that's great. Do we have any other questions from the room here or from online? Looks like everybody's quiet. So let's thank Misha again. Thank you so much for your presentation. I think it's a really compelling vision, and you're still relatively early in your career. So I'm really excited to see what you're going to be doing over the next 30 or 40 years of research. It's going to be amazing, I think. So thank you so much. And I'll send you an email. It'll be great to get a copy of the slides, and we'll share the video with the people who registered for the course that weren't here today. So thank you
Got
so
it.
much.
Thank you again. Thank you for having
Thank
me,
you so
and
much.
everybody have a good rest of your day.
Thank you. And for those of you online,
Bye.
that's the end of our presentations for today and for the course. We've got some people here working at UniSA on doing some project work, but I'll send you all an email probably over the weekend with information about where you can download the slides and the videos as well. So thank you very much for attending, and we'll catch up with you later. Thanks, Misha. Bye-bye.
Bye, everyone.